There we go. All right. That is not the recording. Okay. Hello, everyone. Welcome to lesson number 4 of Optics Academy. This is on aberrations. What could possibly mess with our images, you know? Well, I mean, a lot. It's not just aberrations, but from an optics point of view, those are a pretty big enemy. So, okay. Why do we care about aberrations? If you've been here for, I mean, at least some of the past ones, can anyone tell me what assumptions we've been making for like our lenses and mirrors? There are two that I'm looking for. Any takers?
Does one of them start with a P?
Does it?
One of them is the paraxial approximation, right?
Yep, bingo. That's one. What's the other? The other has to do with geometry. What shape have we been assuming?
Is it symmetrical?
Yes, it is symmetrical. But it's another S word I'm looking for. Going once, going twice, going 3 times. Spherical. So lenses and mirrors don't have to be spherical, right? But they're typically spherical because it's easy to manufacture. But of course, like when you get into like really fancy mirrors and stuff, they're not always. But for our first order theory that we've been doing for like lenses and mirrors, we just assumed spherical surfaces, and in particular that paraxial region. So the, you know what? Let's look this up. So we've been assuming spherical surfaces, and in particular this region. Right. Okay. So types of aberrations. We have chromatic and we have monochromatic. Chromatic means, well, chroma is color in Greek, I want to say, and monochromatic just means a single wavelength, right? So for our monochromatic aberrations, we then have 5 types of primary aberrations. Before we were looking at first order approximation, so there's no aberrations whatsoever, but here we're extending it to third order. What does that mean? Have people done like Taylor approximations, like Taylor expansions? Okay. Okay, nice. So essentially it's where when you Taylor expand something, typically we just do it to the first order. It's a series formula called the Taylor series where, let me write this up. Basically you have f of a, let's say. So you have a function f of x, and a is x equals a is where you about where you want. So like you have f of a plus, and then you have what is it again? I think it's f prime of a. So this is your first derivative evaluated at a times x minus a plus, and then f, was there 1/2? There is a 1/2 here. 1/2 f double prime of a times x minus a squared, and then plus, and then we have a 1/6 f triple prime of a x minus a cubed. So it's a series, right? And it approximates your equation. I mean, not your equation, your function close to this value of x, which is a. and it goes on, dot, dot, dot. But typically, we use it here, up to here, if it's by hand. But yeah, essentially what I was saying is, with our stuff before, we only cared about first order stuff. So this is what we mean, first order. But now we care about, all of the imperfections that are going to affect our image quality. So we are extending this to the third order. So now we are going all the way up to here. That said, of course, if you kept going up to higher orders, there's other there's more aberrations for sure, but they're small enough that these are the main ones that we care about. So this is what I mean. That's hopefully a legible enough thing of the Taylor expansion. Yeah, it's just an approximation that I have to use lots of in physics classes now. But anyway, okay. So we have spherical, which I have alluded to before. We have coma, we have astigmatism, we have field curvature, and we have distortion. Those are the main, they're also called primary aberrations. Those are the main ones that we care about. So, all right, spherical aberrations. Okay, so this is what I talked about for third order. So once we add in some things, and there's some derivations if you want, the textbook doesn't even have it, I don't think. Okay, but if you wanted to do it, what you would end up with is these extra terms. And what does that look like? This is what happens. So when we have our ideal surface, this is our focal point, right here. But in reality, so the closer we are to the axis, the closer we are to the ideal paraxial focal point. But as we go up, this is that H that you see here, you actually end up falling short. So this is, remember that we made the assumption that our surfaces are spherical, right? This is actually a drawback of spherical surfaces. If we actually had a hyperbolic surface, this would not happen. So sometimes you get mirrors for very specialized uses manufactured to be hyperbolic instead of spherical, and they're fancier. So yeah, this is essentially what spherical aberrations are. Coma aberrations. So if you can kind of make out here, what happens is, as we again go to the outer edges of the lens, the further out we go, the more we kind of trail off into one direction. So this is our paraxial regime, right? And let's say those converge to this point here. But the further we go from the axis, the more we've kind of been trailing off in this, in this direction. And the effect is this kind of a tail that happens. You can see it here as well. It's going that way, right? You can see how they should use colors. This one and this one are here, and then this one and this one end up here. So it's going like that. And here, what we're seeing is that this tail that happens. Does that make sense? This is like our lens, and ideally our image would be mapped 1-to-1 like this, but instead, oh shoot, my bad. Yeah, this way, my bad. So ideally, since this is our zero, this circle here will go here, and this circle here would go here. So that would be our ideal 1-to-1 mapping. But instead we're drifting. So that's the coma. It's just coma, or there might be, I don't think chromatic aberrations. I don't know, that might exist, but I think it's just coma. And then astigmatism, if your eyes are bad like me, I have an astigmatism number that is pretty high, I think. And if you talk to your optometrist about this, it comes from your eyeball being like oblong in a certain direction, right? Fun fact, I use contacts for like when I used to do cross country and like, or like when I go skiing and stuff, and mine actually have a very specific orientation that they have to go on my eye. If like there's like a tiny marking close to the edge of it, so it doesn't affect, I'm not seeing through the marking, but like if it's not oriented properly, I can't see shit. So with that, what we have here is you have, they're using all these fancy terms. We have not talked about what the chief ray is, but I think you can appreciate that, you know, here we've split the surface into two perpendicular components. We have the meridional ray and the sagittal ray. It's essentially your surface is elongated in one direction, right? So the effect of that is this meridional is this vertical longer plane that we're looking at here. What we have is, you know, your image will form here, but in your sagittal plane, which is the horizontal shorter axis here, your image will form here. And you can see how there's that discrepancy. So that will cause blurring and like, it's almost like, if any of you have astigmatism, what you see is like, you see like faint copies of like an object or light source, like sort of scattered around it. That's what I see. I wish I could like take a picture through my like bad eyes and show you, but I can't. So okay, field curvature. This one, once again, I'm calling that we have made the paraxial approximation, right? But so usually what we're capturing the image on, whether that's like a projector screen in the classroom or like you know, like a detector, like a sensor, it's usually a flat surface, right? But actually what happens is that the more you go off axis, the point at which your image forms is not actually like, well, both your object and your image. So the object and image planes are actually curved. And what would happen is then that your flat, you know, screen, for example, is going to be not exactly within the focal plane, since your focal plane is curved. So it'll be blurry. So this, what that looks like is, you know, let's say you've placed your object exactly like if you've calculated where you should place your object in your screen, let's say, based on the paraxial location of it, then what happens is you'll have a clear image close to the center, and then it'll fall away at the edges, and you can kind of see that here. And if you were to move this, let's say instead of here, you had, you put the screen right here, then while this part and this part are going to be in focus, while this part is going to be blurry. So this is what you get instead, right? Okay. Distortion is the last of the 5 primary aberrations. Oh shoot, I'm running short on time. So this is an undistorted, let's say, object, and you're looking at this with an optical imaging system. Oh shoot. So the two things that the two types of distortions that are the most common, one is pincushion. You can see how this is like squished together, and one is barrel, where it's kind of like fatter on the center. So yeah, okay, I'm gonna glaze over that. And then chromatic aberrations were the other main category, right? So this is where are different colors, or let's just say different wavelengths, because we're working in, you know, the shortwave infrared region, are actually going to land at a slightly different focal point. Why is this? It's because typically your a material is actually going to have a slightly different refractive index depending on your wavelength. So the effect of it is that, you know, like your red wavelength, let's say, will refract us through it by a certain angle, and your blue is going to refract through by a slightly different angle. And so your blue focus is here and your red is going to focus here. And we don't want that. If you've researched the achromatic doublet, the goal of that is to essentially get rid of chromatic aberrations, because they're also pretty harmful. No, what just happened? They're also pretty harmful. Yeah, typically, I think your typical achromat is like designed to tackle the visible range. So we're gonna have to make sure that it can cover our range for us. I still haven't figured out why that happens. But yeah, that's about it. Yeah, so there's a lot of choices that we can make in the design of an optical system to like minimize aberrations. And how that works is usually you have one element. Well, I mean, sometimes you just straight up design the element differently, but oftentimes the achromatic doublet is a good example. You'll have one component output a certain amount of aberrations, you quantify that, and then you want your next component or another component somewhere after it to counteract those aberrations. So the achromatic doublet essentially does that. The two lenses there basically like cancel out each other in terms of the chromatic aberrations they create. So that's that. I'll leave it at that. Does anyone have questions?
So all the aberrations you mentioned, they apply to both chromatic and monochromatic, right? Like there's monochromatic coma as well as chromatic coma and that sort of thing.
Oh yeah, so these one, maybe this slide wasn't the most clear, but the ones at the bottom, these ones are monochromatic. Essentially, they're not wavelength. They don't discriminate by wavelength, right? But that said, you don't have to be like perfectly monochromatic for this to happen. Like you can have a light source that is like in a fairly narrow region surrounding a wavelength, and these will happen.
Okay, so chromatic is its own thing, essentially.
Chromatic is like when you have like different wavelengths behave differently, and these ones are more geometrical, right? Geometric, yeah.
Right, okay.
Are these effects independent? Maggie asked. Can post-processing adjust for changes in aberrations while we're in flight, or is that already accounted for by component designs? Ooh, those are good questions. Okay, are these effects independent? Yes, but typically you have all of them, right? So the goal would be like, for example, in code 5 to simulate and like be able to predict and then optimize for these aberrations already. So in our design, we want to anticipate for this for sure. In the design of any optical system, you want to account for aberrations, like at least the primary ones. And in terms of post-processing, yeah, I think some of them can be accounted for. But then again, we're already going to have other things to account for, like we're going to have, like, for example, when we're imaging from an angle, that'll give us a fall off, depending on, like, the close end of your image is going to be like slightly zoomed in compared to the far end of your image. We're gonna have like already a series of non-optical things to post process. So the goal would be to do it the best we can here and then leave it to the data processing team to handle other things. So yeah, the exact divide hasn't been specified, but I guess whatever we can't do is gonna be for post processing.
I think one of the easiest things to compensate for is the barrel and pin cushion distortion, because those are easy to quantify. And then the smile and keystone distortions, I think those also arise from aberrations, right? Because the spherical diffraction gratings don't have that problem. So it's a geometry thing with the optics.
Right. Yeah. The way I've talked about things here is just in a typical non-diffractive optical system. For us, when we add in, the push broom diffracting system, you end up with like one spatial, one spectral axis, and that changes the game too. Yeah, like smile and keystone distortions are like specific to like push broom hyperspectral. Well, the combination of them is actually other types of images get them as well, but yeah, okay. I will stop recording here, but feel free to drop any questions if you still have any.